But suppose you have to calculate the pH of a strong, or rather a weak acid or base. We've done this before with strong acids and strong bases, but weak acids are much more difficult because in a weak acid the concentration of the acid is much greater than the concentration of hydrogen ions. And remember, what pH is measuring is not the concentration of acid. It does not measure the concentration of acid, it measures the concentration of hydrogen ions. That's probably the biggest thing that you need to get straight, and that will avoid confusion for you. You have to understand what pH is measuring. It's not measuring the concentration of acid per se. What it's measuring is the concentration of hydrogen ions. And same with pOH. In a weak base, if we were calculating pOH, the concentration of the base is going to be much greater than the concentration of hydroxide ions. The reason it was easier with strong acids, let's say, is because in a strong acid, like HCl, the concentration of acid is going to be equal to the hydrogen ion concentration. So that made our life a lot easier to calculate pHs, because whatever the concentration of the acid was, it was also the H plus concentration. Here, it's going to be different. So this is true in HCl, this is true in strong acids. It's not true in other things. And in fact, these weak acid and base calculations are going to require an ice table. What they really are is they're just equilibrium problems. So we're just going to do an equilibrium problem, we're going to do an ice table, and you're going to have to know the Ka or Kb, or pKa or pKb, and turn them into Kas and Kbs to find the pH of a weak acid or base. So it's going to be a little bit trickier, to say the least. So what we're going to try to do is we're going to try to calculate the pH of solutions of these four things right here. Okay, they're all going to be the same concentration. They're all going to be 1 molar solutions of each one of those. You're going to need table 15 of the data booklet. So I'm going to do this using the other camera, but you may want to jot down these four: methanoic, ammonia, hydrochloric, ethanoic, and 1 molar solutions. Find your data booklet, hopefully you have it, and we'll work on solving these using the camera. Okay, so we are going to try to find the pH of 1 mole per cubic decimeter methanoic acid. Missing an A in there. But to do this, there's a number of things we're going to have to get straightened out before we even get started. Probably first and foremost is what the heck is methanoic acid. When we study organic chemistry, you hopefully will be able to determine that, but for now we can consult table 15, and there's two important things we're going to need from table 15. The formula and the pKa. So I'm going to look up methanoic acid. It happens to be the very first one on the list. I know you probably can't see it on the screen, but if you have your own data table 15, you can find this out. And so we can see that methanoic acid is in fact, and the pKa is 3.75. Now, we've learned about acids. We've learned how they lose hydrogen ions. That's what acids do. They donate hydrogen ions. The methanoic acid formula is written this way to try to show you it's going to lose one hydrogen ion and it's going to lose that one. So if we put it in water, it will lose a hydrogen ion. It will ionize. Now, what the problem is the concentration of the methanoic acid is 1 molar. That's the concentration of this stuff. But we want to know the pH. What I know is that the concentration of hydrogen ions, that's what I need to know. To know the pH, I need to know the concentration of hydrogen ions, not necessarily methanoic acid. I don't know what the concentration of hydrogen ions is for sure, but I know it's definitely not 1. In fact, it's going to be much less than 1, since methanoic acid is a weak acid, and most of it's going to remain unionized. So, to do this, one of the first things I need to do is set up a little equilibrium. I need to ask myself, what is this thing going to do in water? So when we put methanoic acid in water, it's going to ionize some of it, not very much of it. So a hydrogen goes from here to here, acid, conjugate base in this case. So we'll have an H3O+, same thing as a hydrogen ion. and then we'll have what would be called a methanoate ion. So then we could set up a little ice table. We're going to do that eventually, but if I write the equilibrium expression for this, and we'll do that up here, gotta put products on top, so it's H3O plus and COOH minus up there, and then HCOOH, the methanoic acid, goes on the bottom. The water isn't going there because it's a pure liquid. And remember, instead of a KEQ, we actually call this a Ka, just because it's a unique, special circumstance. So what I got to do, see if I can get this a little bit closer for you. Maybe see that a little better. What I got to do is I got to find out what this Ka is. Eventually I'm going to need that in one of the last steps of the problem. So I can go from a pKa to a Ka, just like we did previously in this video a couple of times. I'm going to go 10 to the negative 3.75, and that's going to be my Ka for methanoic acid. So I punched in my calculator 10 to the negative 3.75. Turns out that the Ka here is 1.78 times 10 to the negative 4. So to go from pKa to Ka, Ka is 10 to the negative pKa power, just like I did here. And so now I know my Ka. So I know what eventually is going to go there, kind of in a later stage of this problem. But once we got this figured out, if you understood ice tables to begin with, this is just an equilibrium problem. Now that we've got all this laid out, we've kind of figured out what's going on, we're just going to do an equilibrium problem, and we're going to figure out the concentration of H3O+. Because if we know the concentration of H3O+, all we need to do is take the negative log of it, because pH is the negative log of the hydrogen ion concentration, or H3O+, same thing. So going to make an ice table. Concentration of this is 1. We're just going to ignore water. It doesn't go on the equilibrium expression. I'm just going to put a dash there. And let's just assume that in the initial stages, in the moments after I add my methanoic acid to the water, the concentration of both of those is 0. So I know I'm going to make some amount of product. So we'd call that plus x. And then this would be minus x. So therefore my equilibrium concentrations are 1 minus x, x, and x. Now if you're good at your ice tables, you should be thinking by now about small x simplification, because this is a very small number here, x is very small, and to subtract it from 1 doesn't really do much. So we're going to do the same technique we've done in many other types of equilibrium problems. We're just going to assume that that final concentration of methanoic acid is approximately equal to 1. We can't get rid of all the x's, because the issue is, the reason we can get rid of this x is because it's very small compared to 1, so subtracting it from 1 doesn't really do anything. We're not going to ignore it here, though, relative to 0. So, again, this is just an equilibrium problem like we've done a bunch of before. We're trying to find the concentration of H3O+, so we can find the pH. So, 1.78 times 10 to the negative 4. I'm just putting stuff in my equilibrium expression that I made up here. So 1.78 times 10 to the negative 4 equals x times x over 1. My methanoic acid concentration goes in the bottom. So 1.78 times 10 to the negative 4 equals x squared over 1. The over 1 doesn't really do anything. Technically, I guess we could multiply both sides by 1, but we get 1.78 times 10 to the negative 4th equals x squared. Square root both sides. And so x ends up being 0.0133. Now what is that? That's the concentration of hydronium ions or H plus ions in solution. It's also actually the concentration of methanoate ions. X is both of these things. But what we're interested in is the concentration of H plus. This is the concentration. We just need to know the pH. So to go from a concentration of hydrogen ions to a pH is the negative log of the concentration of the hydrogen ions. So I'm just going to take the negative log of 0.0133. And the pH of the solution turns out to be 1.87. So a little bit trickier, a little bit more time consuming to find the pH of these weak acids and weak bases compared to strong acids and strong bases. It is something that you'll get faster at, and it's something that you'll see there's kind of some shortcuts that you can take. But I'm going to do just one more with you right now, which is the ammonia. So we also want to find the pH of a 1 mole per cubic decimeter solution of ammonia. Now you should be recognizing ammonia as a weak base. It is a weak base. So bases are proton acceptors, so it's going to take a proton. And we need to know the pH here. So we're going to need to know a couple of things. We're going to need to know its pKb value, which we find it actually listed, and it's right there. Its pKb is 4.75. And I'm going to turn that into a kb by going 10 to the negative 4.75 power, because it's the kb that we're going to need in the end. So take out my handy dandy calculator here, and we go 10 to the negative 4.75 power. It turns out that's 1.78 times 10 to the negative fifth. And that is the kb of ammonia. That's the one that's going to be more useful to us to solve this problem. So the next thing I got to figure out is, what is ammonia going to do when I put it in water? So it is a base. Instead of being a proton donor, like in our last problem, a base is a proton acceptor. So a proton is going to go from the water to the ammonia. We're going to form the ammonium ion and the hydroxide ion. And the equilibrium expression, products over reactants, is NH4 plus over OH, products on top, reactant on bottom. Skip writing water because it's a pure liquid. So once again we have an ice table, and you're going to see, like I said, there's some kind of common patterns that end up happening here. Concentration of here is 1. We're going to ignore this, assume those initial concentrations to be 0. So initially there's no NH4 plus or OH minus. Where we're going to go with this, by the way, is we're going to find the hydroxide ion concentration, and we're going to use that to get the pH. So that's my goal here, is try to figure out what the equilibrium concentration of hydroxide is. So again, it's a weak base. This is pretty small. It's not going to ionize much. It's going to ionize a little, though. So our change is going to be x plus x plus x minus x, and then so we have our equilibrium values here. And in this case, this is even smaller. This is a factor of 10 smaller than our last problem, so it's even more sort of correct or okay to use small x simplification. The smaller that your equilibrium constant is, the more valid small x simplification is. So 1.78 times 10 to the negative fifth, we're pretty comfortable with that. So that's going to be approximately equal to 1. So my kb, 1.78 times 10 to the negative fifth. My products go on top. That's going to be an x and an x. That's x squared. My reactant goes on the bottom, and that's 1. So again, maybe a similar pattern you notice to how the last one ended up. We ended up right here with the last one. Very similar pattern on how these weak acid and weak base problems end up working out. This number is not always going to be 1, but this stage is going to be very similar in many of these problems. So x squared is 1.78 times 10 to the negative fifth. Take the square root of both sides. So we're going to square root 1.78 times 10 to the negative fifth. Get out my handy dandy calculator here. And so that's actually 0.00422. And guys, don't forget your significant figures here. These zeros are not significant. The number, the way I wrote it here, only has 3 sig figs. So don't round this to 0.004. You've rounded your number to 1 sig fig. Okay, so let's ask ourselves, what is that? Well, that's the concentration of NH4+, but more to the point, it's the concentration of hydroxide. Remember, we want the pH here. So there's a couple of ways we could do it, but what if we found the pOH? Because we don't know the hydrogen ion concentration, but we do know the hydroxide ion concentration. So let's find the pOH instead, which is going to be the negative log of 0.00422. So log 0.00422, we get 2.37. That equals the pOH. And then we know that pOH plus pH have to sum to 14. So we just subtract 14. We get a pH of 11.63, let's call it. Okay, so I think we will stop there for now, and we'll continue to work with these problems in class. And I know that can be a little bit confusing, so if you're having some trouble with this, be sure to ask me about it next class, and we can go over some more problems. Thanks for your patience, thanks for listening, and have a good day.